Okay, I've got 7:30, so we will, I'll call this meeting to order. And we got a couple of things we got to take care of this, first off. Last meeting, I forgot to get the meeting minutes from October 6th approved. So we're going to have to do two of them today. So the meeting minutes are available in the members area of our website. And so I'll need a motion to get the October 6th minutes approved. Okay, Tom Owen, he has made that motion. Seconder, I saw Jeff waving over there, so Jeff Robertson. Any errors or omissions? If anybody can remember back that far. All in favor? Opposed? Motion carried. So now we can do the November minutes that are available on the members area of the website. Again, can we get a motion? Dennis, okay, thank you. Seconder?
Okay.
Oh, Tom Owen, okay. Any errors or omissions from the November meeting minutes? Not seeing any. All in favor? Okay, opposed? Motion carried. Yay. Okay, next up we have Jeff Whiten to do the treasurer's report. So Frank, if you can get that up on the screen, it'd be much. Oh, he's already got it. Oh, he's got
it. Good evening, everyone. So I can't believe another year is gone. Holy smokes, that happened quickly. So this is my last treasurer's report before I come back in January and provide a summary of our years. When we do our year end, I usually come back in that January meeting and we'll just take some time and we'll go through the whole chart of accounts and give you a little better sense of what we spent our money on in this past year. But as now we're through November, so the general account actually grew over the month of November. We started out with a balance of just about $79,900, and just with membership dues, that balance went up to $80,453. We had a smattering of expenses through the general account in November. They were primarily due to BNLO non-casino expenses, and we had a couple of miscellaneous expenses from our Scope Medic program. The casino account, we're starting to draw on that account a little heavier. This month, you're seeing about a $7,000 reduction. So we started out at 88.4, we're down to 81.6. Those expenses were primarily due to Jasper Dark Sky. There was a couple of PlaneWave expenses that went through, and a contribution that we made to the ISEP program at the University of Alberta. This is a little, I don't want to call it misleading, but there are some significant expenses coming out of the casino account that didn't clear in November that will clear in December. And, you know, that could be to the tune of about $10,000. So you'll see those at the year end. The Bob Drew Fund remained unchanged. So it's still sitting at 2516. I can share with you, though, that we have drawn down on the Bob Drew account during the month of December for the BAMT renovation. So we've been able to spend some of that money, and I'll share that with you when I come back in January. Any questions?
Okay, next up will be our guest speaker for tonight, and that's Dr. Chris Hurd from the Department of Earth and Atmospheric Sciences at the U of A. And his topic is What's the FNCs Finding a Source of Meteorites from Mars? So a little biography on Chris here. Chris Hurd has had the dream of studying rock from Mars since the age of 13. After an undergraduate degree in geological sciences from Queen's University in Kingston, he studied meteorites from Mars for his PhD at the University of New Mexico and worked at NASA Johnson Space Center. Since 2003, he has been a professor in the Department of Earth and Atmospheric Sciences at the University of Alberta. His research includes studies of meteorites of a variety of types, as well as ways of curating meteorites and future return samples under cold and clean conditions. He is the curator of the University of Alberta Meteorite Collection, the largest university-based meteorite collection in Canada, and home of the world's only meteorite curation facility that operates at cold temperatures. He is a return sample science participating scientist in the Perseverance rover mission. So without further ado, we'll bring Chris up for his presentation.
Thanks. Well, it's nice to be back, and I'm actually quite pleased to be here to talk about. I'm just setting a timer here for myself, because as some of you know, I will drone on. So it's nice to be here to talk about this particular topic. I actually started thinking about this question in earnest during a sabbatical in 2017. So, and this paper that I'll mention here was published last year. So that's a 7-year project. There was a whole host of people involved, as listed here on this slide. Former students, colleagues, some of whom who have since passed away, actually. So you'll see why that is as I go through this. Need a lot of expertise from different sources. I'm going to apologize ahead of time. I can't stick around for the break or the second half of the meeting. I have a basketball game to get to. So, but I will take some questions after. If there should be time, I'll try to leave time for questions. But my email is there as well, and I will answer that email. Any questions you might have about meteorites from Mars. Okay, this is topic was partially inspired by the Mars at the Matart event that I spoke at in April. And here are some of Murray Paulson's Martian meteorites. And he actually has, I think, a couple of the same ones, right, Murray, that were on display here. I think you've got them here with you. So at the break, check it out. I highly recommend that if you want to see some actual slices of meteorites from Mars. It's kind of amazing that we can actually hold a piece of Mars in our hands. And I've talked about getting samples from Mars into this audience before, but I did my study of Martian meteorites for my PhD because those are the samples that we have until we actually bring some back. So a bit of a brief history of Martian meteorites. They were known, still are generally known as SNCs after the first 3 meteorites that turned out to represent sort of 3 subgroups. And they were all false. That is, where there was a fireball witnessed and then rocks were picked up afterwards. The first one was actually Chassigny in France in October 1815, and then Shrigati in India in 1865, and then Nakhla in Egypt in 1911. Then there was another one in Zagami, Nigeria in 1962, and that Zagami looks very much like Shrigati. And then you had other ones like Lafayette and Governor Valadares that were found, and they were able to be grouped together by similar rock type, similar lithology, as we say, to Nakhla. And then these other ones with the sort of combination letters and numbers were found in Antarctica. And by the mid-70s, there was a concerted effort to recover meteorites from the Antarctic ice sheet, and that's where those names or those sort of codes come from. And they were grouped into Shrigati. So those were known as the Shrigatites. And then Nakhla gave rise to the Nakhlites, and then Chassigny to the Chassignites. So you still do see some of that same, and you'll see that same terminology. But where they came from was not clear. They were all oddballs. I mean, the first one was 1815. It was not long. It was about 10 years after l'Académie Française said we could even get rocks from space. So this was early in the history of even recognizing what meteorites were. But they had characteristics that told researchers, even back in the 1800s, that these were different. Something else was going on. These are different rocks from your chondrites or iron meteorites or other meteorites that we have. So there are all these kind of oddballs and just known as SNCs until these 3 key papers. Now, Reed and Bunch is quite interesting, and I really wish I had a chance to talk to, because I did know these authors before they passed away a few years ago, but to ask them, but they never actually came. They did a study of the Nakhla meteorite, and they concluded, based on its geology, essentially its petrology, that is the history of that rock, that it must come from a magma that crystallized on a pretty sizable planetary body, somewhat like the Earth. Okay. But they never came out and said Mars. And I wanted to ask, like, did reviewer number 2 tell you that you couldn't say Mars? Right? Most of you who published papers, no. Did reviewer number 2 say, no, you can't? And the editor agreed with them. Because they were basically this close to saying that this rock's from Mars. Then along came, of course, there was thoughts, a lot of stuff that is in, conference abstracts or even just people talking about these things, a lot of interest in it. Of course, it wasn't until 1980, McSween and Stolper, who wrote this paper in Scientific American that I've taken a snapshot from, that go through the whole sort of range of possibilities of places in the solar system where these SNCs could come from. And they say the only alternative source of these Shergottites in particular that we find appealing is Mars. And talk about it. Mars is a igneous planet based on Viking and Mariner photographs, like it says there. And so it's almost like ruling in, ruling out. They ruled out other possibilities and said it must be from Mars. Now, Bogart and Johnson then did this key study where they looked at gases trapped in this one particular meteorite, EET 79001. So EET stands for Elephant Moraine in Antarctica. 79 is 1979 field season. 0001 was not the first one found. They didn't get lucky. They just processed that one first in the lab at NASA Johnson Space Center. And so that had been in the lab for at Johnson Space Center for a few years, and Bogart and Johnson started looking at gases they could extract from this rock and comparing it to the atmosphere of Mars as measured by the Viking landers in 1976 and following. So we had the data from the analysis of the atmosphere of Mars and then the data from the gases trapped in the rock, and they showed that it's a match. So this is the Elephant Moraine 701 meteorite after it was sawed in half. And then on the right is a NASA image of one of the Viking landers to sort of represent that connection. But in detail, in fact, those black spots that are in the left-hand image, there's sort of these centimeter scale black spots in there. Those are actually where the gases are trapped. And I'll come back to what those are here in a minute. So it's a match. Now, the other thing, and it's a match in different things. It's a match in the relative proportions of the gases. It's also a match in terms of the isotopes. So the isotopes of argon in particular, 36-38 ratio. That's just one ratio that's shown here. One of the key things is that, yes, it matches the atmosphere of Mars as measured by Viking. And then in this actually shows how Mars MSL, the Curiosity rover, also measured it to greater precision, as shown on the right-hand side in 2013. And then those overlap with the Martian meteorites. But the other thing is that the Martian atmosphere is different in this ratio and other ratios from other places in the solar system. So it's a fingerprint to Mars specifically that allows us to say these meteorites are from Mars. Okay, this is what they look like in hand sample. That's a centimeter cube there on the left in the center. And so you can see individual crystals in there. You can see this dark vein going across. I'll come back to what that is in a second as well. And then we can also see what they look like in thin section on the right-hand side. That's a 1 millimeter little scale bar at the lower right. And shows how they have millimeter scale crystals of minerals that we recognize, like pyroxene and plagioclase, that are familiar to us from igneous rocks on the Earth. And that's really what they are predominantly, and you'll talk about why that is, but they are predominantly, this is the sort of family portrait of Martian meteorites today. And that link at the bottom, or that website at the bottom, provides kind of a running list. There's a couple hundred kilograms of Martian rock on the surface of the Earth in the form of these meteorites. Now, we say 210. If you go and search up Martian meteorites in the Meteorological Bulletin database, for example, you get closer to 400. But what happens is that website and other people try to pair them together to say, these are basically the same rock that or the same meteoroid, if you will, the same bit of Mars that has come off the surface and broken up in space and fallen, in different places and different times around the world, but there basically was the same rock. And you can do that with enough sort of in-depth look at some of these samples. They generally fall to 5 different groups. By far the biggest, the percentages there in brackets are the by number, how many of those 210 fall into that category. So these Shergottites There's 85% of all of the Martian meteorites fall into that category. Knocklights and shastignites, about 12%. A relatively recently discovered group called augite-rich basalts, about 2%. And then NWA 7034, also known as Black Beauty, and its pairs, there's only one rock like that. And then Allen Hills 84001, there's only one rock like that. So there's a preponderance of the Shergottites, Knocklights, Shastignites. So the SNC sort of holds true as being the main types of rocks that we have. You also see there under each is the ages in millions of years. So that's a really key point as well. The Shergottites all range from mostly about 165 million years to maybe 300 or so, some of them going up as old as 800, but most of them are quite young, geologically speaking. Knocklights and shastignites are all around 1,300 million years, or 1.3 billion. And then augite-rich basalts are 2,400. Black Beauty, or NWA 7034, was assembled about 1,500 million years ago, but it has bits and pieces in it that are as old as 4,400 million. And then Allen Hills 84001 is 4.1 billion years old. They tell us that as igneous rocks, even if you don't know anything about geology, you might be able to see that there's some differences here, but largely they're similar in that they have interlocking crystals that suggest and tell us in detail that these are igneous rocks predominantly. And the oddball is the lower middle there, which is a breccia, bits and pieces of rock that have been reassembled, but everything else is igneous rocks. And so the information that we get first and foremost is from is knowing that these were at one point magmas coming up from the interior of Mars, and maybe, forming these as shown by the sort of ovals here, crust mantle boundary. They're showing some magma bodies that would start to crystallize some crystals of certain minerals that would then get carried up along with the magma up to the surface. Other things can happen, erupts at the surface, has that record of that whole history from where it melted from the mantle right up to where it crystallized on the surface. And that we do this with igneous rocks on the Earth and lots of different environments on the Earth. But the other key thing that these have in them are shock effects. And I alluded to these before. They have melt pockets and shock veins. And on the left, it's a little hard to see, but basically you see a number of little crystals, and they're sort of shown in those inset images on the lower left, those tiny crystals that look sort of dendritic. They form quite quickly during rapid cooling of something that was molten. And in some cases, and these are shock melt pockets, these form as a shock wave passes through the rock, most likely during the impact event that launched this rock off the surface of Mars in the first place. There's energy dumped into the rock. In the case of pockets, we think that there might have been an open fracture even, or maybe like a vesicle or something, a bubble from the original igneous crystallization that collapses as the shock wave passes through the rock. And the energy kind of gets dumped into that area and then melts and forms a melt, which then will either quench into a black glass, which is what those centimeter scale things were in that other meteorite, Elephant Moraine 7001 were, or start to sort of partially crystallize like shown in this left-hand image here. And you think about that, if it was an open fracture or something, that's a very convenient way to get Martian atmosphere trapped inside the rock, because there's atmospheric gas in that open fracture, and then you get this almost instantaneous melting event, and the atmosphere basically gets dissolved into the melt, which becomes a glass. And that's what Bogart and Johnson were actually analyzing in that original Elephant Moraine 79001 meteorite. The other thing we get are shock veins, which is shown on the right there. That one's quite large by comparison. Usually there's very thin, narrow veins. And we can get the key thing here, and this is actually one of the big take-homes from my talk, is that we can get information by studying these features that have overprinted the igneous characteristics of the rock that allow us to say something about the impact event that launched the rock off the surface of Mars and start to get at where it came from. So our understanding of how Martian meteorites become Martian meteorites is shown here. There was another artist's impression that I used for a number of years, but it showed a layered sedimentary rock with green slime on it. And I thought, well, that's not really accurate, because these are not sedimentary rocks with green slime. These are igneous rocks. And also this depicts, so I had a student, a summer student, Maria, a couple summers ago, who was working with me on a summer project, but she has a minor in fine arts. So she painted this painting, this beautiful oil painting. And I've annotated it here a bit. What basically it shows a flash of light on the surface of Mars, which is an impact. And the zoom in shows you that rocks near the point of impact get accelerated fast enough, shown by the circled rock in the upper right, to leave Mars gravity, head in towards the inner solar system, and then if we're lucky, cross the Earth's orbit, fall to the ground as meteorites. Now, we didn't always know exactly how this worked. In fact, when in the 1970s and early 80s, when these researchers were trying to figure out where these SNC meteorites were coming from, the physicists, all due respect to any physicists in the audience, did not know how this could happen, okay? Because an impact is a very energetic event. And all of the modeling at that point said, well, you could never get a solid rock off the surface of Mars. You would just vaporize it, okay? And it's true, in most impact craters, the rocks get vaporized. But Jay Milosh figured out in 1985 in this key paper that there's a specific set of conditions that occur right at the surface that can give rise to a spallation zone, which basically has to do, I won't get into the details, but it basically has to do with the shock wave coming from the point of impact. The actual point of impact in an impact crater is actually below the planetary surface. So think of like actually below ground nuclear testing after the Second World War provided more insights into this process, because the actual point of sort of radiation of energy comes from below the surface. So think of it kind of in the sense that you've got this energy, these shock waves radiating from the point of impact, and they can either positively or negatively interfere with each other for rocks like in the left-hand side that are at point A or point B, essentially. And so what that allows you to do is to accelerate the rock fast enough without it seeing a peak pressure that is, because the shock wave can be considered as pressure kind of squeezing, without seeing the maximum pressure. In other words, the maximum pressure that would otherwise destroy the rock. So Jay Milosh figured that out. And then since then, other more sort of developed modeling has taken place, and we have this concept called dwell time, which is shown on the right. So so the left sort of shows the way that we can figure out how these things get lofted off the surface. And on the right is the concept of the dwell time, which is essentially the amount of time that the rock spends at that peak pressure at some multiple gigapascals, 25, 30 gigapascals type thing, for some fraction of a second, typically. And the thing is that now what we can do is that we can go into the rock and look at these shock veins, and we can model what was happening as the shock vein formed. As the shock wave passed through the rock and formed the vein, especially if you get nice thin veins, they can give you information essentially on the pressure, temperature, time history of the rock. What pressure did the rock achieve? What was the maximum pressure? What temperature did it reach? Obviously, if the vein was molten, it would be molten. But then how quickly after it was molten did it quench? Did it cool off to become a glass or crystallize into something? So we can get that information from the meteorite itself now, from this shock overprint on the rock. Okay. Now, I'll just take a minute to talk about a little bit about what these rocks tell us. And so the cool thing, this is sort of a cartoon version of another cartoon version of what I showed you before, but you melt magma out of the interior of Mars, and they do things on the way up to change the composition a bit, and then they erupt at the surface at different times. What's really cool, interesting about Martian meteorites is that we think that they're mantle sources, that is, the spots that in the mantle where the melting took place, were established 4.5 billion years ago and remained largely unchanged since that time until the point where the melting took place. So, and the best way to do that is through something called a magma ocean. So basically it's a concept coming out of a study of the moon to try to explain the moon's crust and its features and some of the things that we learned from the Apollo samples. But basically you need to take you need to melt the the planet down to several hundred kilometers depth to form a magma ocean. And then that magma ocean acts like a gigantic magma body and sort of differentiates into different sort of different parts of the mantle with different characteristics. So we can actually see this in these meteorites, which is pretty cool. But nothing basically happened in those areas in the interior of Mars since the time that they were set up 4.5 billion years ago, until the time when, say, a meteorite was, or a proto-meteorite, if you will, was formed by melting 175 million years ago and erupted at the surface. So how do you do that? Well, you do it through these mantle plumes, these hot areas in the mantle that where material rises up, or heat rises up, and then you get some melting. Okay. We also get insights into the early crust of Mars from this NWA 7034, also known as Black Beauty, and its pairs. I alluded to this. It was assembled about 1,500 million years ago, but it contains clasts, including a mineral called zircon, which is easily dated to 4,400 million years. So this rock is made up of chunks of the early crust of Mars. And it shows very little water alteration as well. So it obviously comes from part of the surface of Mars that's been fairly unaltered. Okay, this diagram here is another way of looking at the meteorites. It's just a compositional diagram. It's a way of sort of showing different things, but SNC is the lower middle there, between 45 and 50. Yeah, in the blue. Thanks, Frank. And then the augite-rich basalt at 2,400 million years, that's shown by a red cross. And then NWA 7533 is close to Mars' upper crust. That's one of the other meteorites that's paired with the Black Beauty. So those are the ones that we have that are in the Martian meteorite suite. All the other dots on here are from rover missions that have analyzed these rocks at the surface of Mars, and you get very different compositions. Okay, and the ages, although they're inferred ages for rocks on the surface of Mars, they're not known for sure because we haven't brought those samples back. The inferred ages are much different. So we can say that the meteorites are not representative of the Martian crust. Okay, so that's an important point. And more importantly, our understanding now, especially now that we have 210 of these meteorites, as opposed to the handful that existed at the time that Bogart and Johnson did their work, we can say that there's a sampling bias in this meteorite suite. And the reason for that is exactly this, what's depicted here. You have to have an impact on the surface of Mars, and it's a very energetic event. So it follows then that 85% of all the Martian meteorites, or shergottites, are young igneous rocks with these nice interlocking crystals that haven't sat on the surface of Mars for very long, that haven't been exposed to much liquid water, if any. Right. And even those rocks like Allen Hills 84001, which is much older, and Black Beauty, they have a certain sort of competency to them. They have a certain hardness to them that comes out of their geologic history. There are rocks that we have seen on the surface of Mars that are very crumbly, from the rovers, I should say, that are very crumbly, that would never make this trip. That's another key thing. And we do not have any sedimentary rocks in the Martian meteorite suite, even though we've seen sedimentary rocks on the surface of Mars. So we now know that there's a sampling bias. A number of people have written about this. There's a sampling bias that we're getting really only the youngest, predominantly the youngest igneous rocks from the surface of Mars. Okay. So on the one hand, that's not good, because what we want is, and we don't have field context. Okay. So we don't have, this is taken from field school that I taught for a while. These are stromatolites. This is the evidence of ancient life over a billion years ago near Cranbrook, BC. But we don't have the field context for the Martian meteorites. All right. And this right here, and we don't have sedimentary rock. So this right here is an argument why we need sample return, right? And I've talked about this before, but the Perseverance rover is doing that right now. We've just gone over 41 kilometers. It's the first step in Mars sample return. We collected 27 rocks, 2 regolith and 1 atmospheric sample so far, and we have a few more sample tubes to fill. Okay. But the early sample return for a while was going to be 2033, and now that's up in the air. So in the meantime, so basically what I'm getting at for the rest of this is, in the meantime, while we're waiting, can we figure out where these Martian meteorites came from? Can we actually get a bit of field context for where they may have come from. Okay. There have been a number of other attempts by other workers in the past to link these Martian meteorites to the surface. Now, one of the things that could be quite tempting, and what these authors did, was to say, okay, well, we'll do like other people have done with asteroids, like with Vesta, right? You might be familiar that HED meteorites probably come from the asteroid 4 Vesta because they have a reflectance signature in the visible to infrared that it can be matched to, telescopically can be matched to, crushed up meteorite in the lab, right? And you can say these look very, very similar. So these authors tried that with a map of Mars and this Omega MX imager on Mars Express. And they took the laboratory Martian meteorite spectra and looked for places on Mars where it would match. Okay. And you see there's lots of places where it matches, but they're all in the southern hemisphere, which is where old rocks are. Okay. And that doesn't make a whole lot of sense because the Martian meteorites I just told you are really young. Now, there's two problems with this. One is that Mars is an igneous planet, and really what you're seeing in these spectra are the spectra of pretty typical minerals that are in igneous rocks like olivine and pyroxene. And that's everywhere on Mars. And so you could argue that there's not really a unique spectral signature for Martian meteorites. The other problem is that this map, which I've superimposed or registered directly, the red on this shows where the dust is. Okay. So if I go back here, you can see none of those places where they find matches are places where there's dust. And the places that are most dusty on Mars are Tharsis and Elysium, where the young igneous rocks are. So basically, the places where you should be looking, you can't see what the spectra are very well because there's so much dust in those locations. The better way to do this is what actually Pete McGinnis-Mark and colleagues did back in 1992 in this paper, and they said, okay, we have a handful of Martian meteorites, and we now know that they're young igneous rocks. They're probably from a place like Tharsis. So then they looked at, now at the time, we hadn't figured out the modeling completely. So they said, okay, the physicists say you need a 100-kilometer diameter crater. We'll just order of magnitude make that 10. Okay, and we'll just say, let's go with 10 kilometers and look for anything that's at least 10 kilometers across on Tharsis, and they find a handful of them here. There was also this assumption that all the Martian meteorites came from one single source crater. We since know that that's not the case, but this was a good start. Okay, so what we have done in this paper, and we just published last year, is we recognize, first of all, and the upper right there shows you really this bias, okay? This shows you, of all of the meteorites from Mars, 98% are what are called Amazonian in age. The Amazonian of Mars is anything less than about 3,400 million years. Okay, so 98% of all of the meteorites by number are young like that. The surface of Mars, 75% of the surface of Mars is older than that age. So if that doesn't, drive home the fact that there's a bias, I don't know what does. So they're biased towards these young igneous rocks. Okay, and then the diagram here is based on an updated compilation that my grad student Alex Sheen did as part of his PhD, and then we incorporated it into our study, which is along the bottom is the crystallization age, and then along the y-axis is the ejection age. And the ejection age is essentially the amount of time that rock spent in space between when it left Mars and when it came to Earth. And you can see you can group them together. So you can group them, and we've just labeled them here as groups 1 through 9. But you can group them. You can say, so we have this group 3 where the crystallization age is all around 2,400 million years, and the ejection age is 1.2 million plus or minus 0.2. The other thing you can see is you look at the crystallization age, it goes way out to 4.5 billion. The ejection age only goes to about 20 million. Okay. And that tells you that there's a small number of impact creating events that have occurred in the last 20 million years that have delivered all of these meteorites. So we, through all this careful analysis, we come up with, groups 1 through 9, we split 5, 1, 2. So there's 10 distinct events within the past 20 million years. Okay. So that means we're looking for 10 impact craters that have delivered all of these Martian meteorites. Now, we don't have these data. We don't have crystallization age and ejection age for all of the Martian meteorites, but we can group them together for the ones that we do have. The Shergottites all were ejected less than 6 million years ago, and the Nautilus and Shastinites were all ejected right around 11 million years ago. Those are the ones that are sitting at group 7 there. So what do you need to find then if you're looking for the source craters of these meteorites? Well, if everything was ejected within 20 million years, then you're looking for young, fresh impact craters, because that's really quite recent. So you're not looking for things that have impact craters that have been degraded or eroded. You're looking for things that look like they formed yesterday, geologically speaking. Now, fortunately, my colleague Livio Tornabene at Western University in Ontario had been working on this problem for a while, and he has a database that he has maintained of over 300 craters that he uses specific features to determine whether it's a fresh crater, and he has a ranking system as well, like 1 through 5. So 300 craters, and then he has criteria for determining which of those are really the freshest craters. So we said, okay, well, that's great. Those are the ones that we need to work with, because those are the ones that are going to be most likely to be the sources of Martian meteorites. Okay, now one other thing as a bit of background, when we do dating of planetary surfaces, when we don't have a sample that we can bring back to the lab and get an age from, what we do is we take a surface of a planet and we look at all the craters on that surface and we count the number of craters of different sizes, and we essentially use the lunar cratering record as established from the mapping of the moon and the samples brought back from specific locations on the moon that calibrated that cratering record, and we extend it to other planets. We assume that you had lots more impact cratering early in the solar system's history, and it's petered out ever since. We basically extend that to other planetary bodies. So that's what we do for Mars. So then we can say, okay, we're going to go to Mars. We're going to look at a particular area, and we're going to count all these craters, and they fall along a line like shown with these red X's. And then we get an age of about 1 billion years in that case, or just under 1 billion years. And those lines there are where the calibration comes from the lunar cratering record. Now there's different models for this as well. I'll come back to that point at the end. But that's how we do it. Now, that can be a difficult thing and tedious to do. So another part of this study was collaborating with Gretchen Benedicts and Anthony Legain at Curtin University in Australia, who had developed machine learning for this purpose to essentially kind of make sense in retrospect. It's how much machine learning can do these days. But at the time, just getting machine learning to recognize circular features and count them and categorize them was the challenge, and they did that with a crater detection algorithm. And they applied this to Mars, and they mapped 90 million craters on the surface of Mars, okay? Now, there was a crater database already that somebody had done by hand in the 80s, all respect to them. But they were able to do this in a very short amount of time. And then, so it does two things. First, it allows you to do rapid crater counting of those surfaces, and also to identify rayed craters. So this is a little hard to see, but in these color images here, these are 2 craters. The top one's called crater Tooting, and you can just maybe make out these sort of in these blue-green sort of lines coming from that green diamond there. You can make out these rays. Now, rays are really important because rays tell us that in the impact event, you didn't just form an ejecta blanket close by. You actually got things going on ballistic trajectories that went out, in some cases, hundreds of thousands of kilometers away. That we call those failed meteorites, because they made it up into the atmosphere and fell back down. But it's a strong indication that that same impact cratering event, some proportion of those rocks would get ejected fast enough to leave Mars gravity, would become meteorites. So it allows you to really identify those rayed craters, and also to use this algorithm to get the ages of the surfaces. Okay, so our approach in a nutshell was basically to say, okay, we have if we're looking at a map of Mars like shown here, these are all the surface age. This is a map of Mars with the surface age units that are Amazonian, that is less than 3,400 million years. So all the young stuff. And you can see Tharsis on the left and Elysium on the right, highlighted in red as volcanic areas, because that's, we think, must be where the Martian meteorites are coming from based on what we know about them. So then we take that, we overlay all of these nice, well-preserved impact craters from Livio's database. And when you do that, you actually go from 300 and you say, okay, we're going to only look at the volcanic units. And you go from like 300 down to, and you take to 40. Okay. So all of a sudden you're going from 300 potential craters down to just 40. And then if you take the freshness index that Livio provided, like the freshest craters, you get 15. All right. And we're only looking for 10 events. So now we have 15 freshest craters that we can focus our attention on. Okay, from that point, then it gets into the meteorite specific work. So then you got to figure out with some impact modeling, how do you take that 15, those 15 craters that could be the sources for any of the Martian meteorites and get it down to some smaller number. So, and this is where you use the crater detection ages to then say, okay, compare the igneous age of this meteorite to the surrounding area around this impact crater and see if it's a match. And you can also use the crater detection algorithm, by the way, on a crater itself, because you get little other craters that form on the ejecta blanket. So you can actually date the age of an impact crater, even a young one, through this process as well. So you can compare that to the ejection age. So you're basically trying to match things up that way. Okay. Now, the beauty of it, the missing link in all of this is it comes back to being able to relate that shock damage in the rock to the model. And this paper by Bowling et al. Out of Jay Malash's group, published in 2020, I call the missing link, because what they're able to do is to model, and the left, you're seeing essentially an object hitting the surface of Mars, and all that heat or that heat map is basically showing you what happens during the impact. But that little slice there in pink, where it says escapes from Mars, is zoomed in the upper right. And that sort of scalloped out area, that's the stuff that escapes from Mars. So a very thin little layer, relatively speaking, escapes from Mars. What this model is able to do is to say within that layer of stuff that gets ejected, this is the range of dwell times and peak pressures that you get. And we get the dwell times and peak pressures from the meteorites, from the shock damage in the meteorites. So that's why I call it the missing link. So that little slice that's now on the upper right there, it says pressure is consistent with Zagami. That's basically saying for this particular impact event example, that's the slice of stuff that would produce a rock that has the characteristics of the Zagami meteorite. So you're able to then link those back to each other. And then by doing this a bunch of times with different size impactors, you can then say, there's a range of crater sizes that would produce the Zagami meteorite, because there's going to be a lower limit and an upper limit to the impactor size that's going to produce all of the ejecta that would have those characteristics. Okay, I'm not going to get into this table, but except to say that these were the 6 meteorites that we investigated. And then all of these numbers basically lead to what you see on the right, which is N is the number of potential impact craters for a given meteorite. So the very first one, Elephant Marine 78001, there's our old friend that gave us the evidence it was from Mars in the first place. We can basically use its characteristics, the modeling, to say that of those 15 impact craters that we identified as being potential sources, 10 of them have the characteristics that match for this particular meteorite. And then you can see, you go down the list, 10, 8, 10, 11. And then the bottom 15, that means, and 15 means that we sort of really constrained, because for those 2 meteorites, we don't have a whole lot of constraints, but we still we can look at all of those 15 impact craters as potential sources for those meteorites. And the other thing to note is that the model is very sensitive to the depth. And you can kind of see that here, because essentially if you get, this little sliver near the surface out of the stuff that's near the surface anyway, that's sort of the top of the top stuff, then the model is actually quite sensitive to that depth. So that'll be important in a minute. So out of the model comes the potential depth of the rock before it got ejected from the surface of Mars. All right. And then at that point, then you're starting to go in and mapping these impact craters. So here's an example of one that we did. This is called Chakpar. It has a diameter of 19.6 kilometers. It's in Tharsis, northeast of Escraeus Mons. And you can see the lower left there. This is from a map that my former student did. And then the inset image, you can actually see the sort of greenish maps out the ejecta blanket. And then there's this sort of red hashed thing that's basically a lava flow that comes out from underneath the ejecta blanket. Now, Legan et al. Used their crater detection algorithm to then get an age for the crater and the surrounding terrain. And the crater age is about 500,000 years, 0.4 million years. And the surrounding terrain is 540 million years with some error bars on it. The only thing that we found out of our groups of ejection paired meteorites that matches is Elephant Moraine 7001. It's the only one that has an ejection age that's close at 0.6 plus or minus 0.1 million years. That's closest to that crater age. But then the igneous age is a lot younger than the surrounding terrain age. You say, well, what's going on there? So the only way we can reconcile this is to say, well, actually, Elephant Moraine 701 is not from the surrounding area necessarily where you get the average age. It's from that lava flow that comes out from underneath the ejecta blanket that was mapped. Unfortunately, it's too small to kind of get one of these crater counting ages, but it's obviously younger. It sits on top of everything else, and it comes right out from underneath. So that impact obviously hit that lava flow. So we think, and then the burial depth from the model is only 8 meters. So we think that the Elephant Moraine comes from that lava flow adjacent to this impact crater. Okay, Tooting is another crater with a funny name, 23.2 kilometers across on the west side of Olympus Mons. Now, Legan et al. Found that this surrounding terrain was 308 million years and the crater age was about 1 million. And what we find is that T-Cent is part of this group that was ejected around 1 million years ago, but it has an igneous age of 570 million years. However, it's not the youngest one in this whole suite, the youngest igneous rock in this whole suite. The youngest one is 348. There's a number of them. They're all linked together, ejected about 1 million years ago. The youngest one that at least has an age is 348, which matches very well with that surrounding terrain age. And the other thing is that our burial depth for our model for T-Cent is 26 meters. It's deeper. So it fits with the idea that T-Cent was part of a lava flow that was buried at greater depth. And you have a series of lava flows above it. I think and it corroborates what Legan et al. Found. So it sort of looks like this. So you have T-Cent there in the middle. And then you have all the ones that have ages kind of go from, younger and younger, with the youngest one, NWA 1195 at 348, which is the same as the modeled age for the surrounding terrain. And there's 26 meters depth. Now, one interesting thing is that these other two that are in gray at the bottom, those are those object-rich ones that have been dated at a different age of 2400. And Lapin et al. In 2017 suggested, because they had very similar ejection ages, they were around 1 million years, they were all ejected in the same event. However, our results show that the NWA 8159, which is sort of shown there at the bottom schematically as maybe being a lower down in the stack, is not. It can't be. Its burial depth was at most 5 meters and more likely 2 meters. So these are not from the same impact event. So there's an additional information you get. And ultimately, we think we might be able to do sort of pre-impact stratigraphy if we do all of this with enough meteorites. Okay, I'll skip over this one, and I'll skip this because I summarize it on this slide here. This is basically another map. This is from the Atlas of Mars. So it shows maybe a little more intuitive. But again, Tharsis on the left, Elysium on the right, with the colors showing the igneous units that are all Amazonian in age, so 3,400 million years at most. And superimposed on that are the 5 impact craters that we identified out of our study that are most likely the sources of a subset of the Martian meteorites. On the lower left, there is Karatha and Greteri. These are 2 other impact craters that were published by other people. Those are on older terrain. Those are the ones that's Black Beauty. Even though it was assembled at 1,500 million years, it has these clasts in it that are really, really old. And then Allen Hills 84001, which is 4.1 billion. So those are coming from much older terrains. But basically we've then postulated these 5 impact craters as being the most likely sources of 5 of those groups of Martian meteorites. And in the supplemental material of our paper, we suggest this potential source craters are a couple ideas for the remaining 3. So we're really close to getting all of them. Okay. Which is exciting because we're enabling us to give us field context for these meteorites. Jezero, where Perseverance is there, and that's a very different environment. And we're getting sedimentary rocks, and that makes sense because those rocks we're getting with the rover, we could never get, most likely, from the natural ejection and delivery process. So it was published in Science Advances last August. It's open access if you're interested. And I'll just leave you with a couple of implications. First is actually linking the meteorites to their units, yes, but to their volcanoes, and testing the models for those volcanoes. So on the right is an example of a really detailed study that was done on small vents on Tharsis, and Chakpar crater is right there in the middle of it. So we might even be able to say with careful mapping what the actual vent was that produced the lava flows that produced the Elephant Marine 701 meteorite, for example. But also being able to test this. Some people think that there was a big magma body underneath all of Tharsis. Well, we could potentially test that with this if we know that these meteorites representing lava flows are from specific areas within these igneous regions. And then the other thing is that I mentioned there's different ways, there's different models of extending that lunar cratering record to Mars. And that's sort of shown here. The 2 models are shown by the 2 lines. And the uncertainty is east-west, essentially. The greatest uncertainty is in the box here, in the same age range that the most Martian meteorites are. So if we can actually then turn around and say, okay, this meteorite comes from that lava flow, and that meteorite is 175 million years. It raises the potential of actually being able to say, to calibrate, or at least add a pinning point to the calibration for Mars specifically. And again, the rocks we're getting with Jezero from Jezero with Perseverance for the Mars sample return are much older than that. So they're very complementary bits of information, and would also help us to calibrate this crater chronology. And then the other thing is it's a framework. It's a framework in which to study all Martian meteorites. Our sources are testable. We need, and this drives a lot of the research that my students are doing now, is if we can we get a new Martian meteorite that you find, can you constrain its dwell time and injection age and crystallization age? Can you get this key information? If you can maybe link it to one of the groups that already exists, and then therefore one of the other craters that it may have come from, and link it to, and because it's sensitive to depth, do this pre-impact stratigraphy, basically piece back where those Martian meteorites were before they were ejected from the surface. And then the other really cool thing is that there are 15 impact craters that we identified, fresh impact craters. These could all be sources of meteorites. So it raised the interesting idea that are there other source craters from which meteorites have yet to be identified? So a good example is this one, Zunil. It has big, long rays. Its crater age is 0.4 million years, but the surrounding terrain is only 30 million years old. Okay, really, really young. There's no meteorites of this age. Nothing matches. And so possibly, maybe the surface is not amenable to certain things about the surface that modeling shows, sort of need to have particular characteristics to be able to eject things. Maybe they're out there in space and haven't arrived on Earth yet. Maybe they're just sitting in the desert somewhere and haven't been found yet. So that's a really cool idea. So we've identified basically the likely source craters for 5 of the 10 ejection paired groups of Martian meteorites, essentially. And it's a testable network. And, as a curator, this is our specimen of the T-Cent meteorite. We have the locality on the Earth where it fell and was found, have a specimen number. Maybe we can actually say now that its original origin is Tooting Crater, Olympus Mons on Mars. Thanks.
Any questions for you? Do we have any questions for Chris? Frank got nothing.
Thank you very much for a really interesting talk. Do you think that it is, in general, trickier to pinpoint the source crater of a Martian or a lunar meteorite, and why?
That's a great question. I have a student working on the lunar meteorite component. It's challenging because there are even more impact craters on the moon, and because the gravity is less on the moon, it takes less to eject those samples. So it's much more of a needle in a haystack situation, actually. What we're trying to do ultimately, my one PhD student is trying to develop more of the modeling framework. So not only the pressure temperature time history, but in more detail. So trying to get at things like the temperature history, because sometimes what happens, you get the shock veins forming. Ideal case, you get a thin shock vein. The pressure wave is still there when something crystallizes from that vein, and you get a high pressure polymorph, so a high pressure version of olivine or something like that. And you get really a lot of good information from that. But that's not often what happens. You get sort of back reaction because there's, sort of heat left over, that sort of thing, and you get a reaction. So trying to sort of incorporate all of that. So more modeling in that regard, I think, is what's needed. But I think it is possible for the moon. It's just a slightly different problem, if you will.
Any other questions? And I don't see anybody online. I think that's it for tonight. So I'll thank
Okay.
Brett.
Thank you.
And for token of appreciation, we have a book from the library that we think you might be interested in.
Thanks so much.
Okay, thank you, guys. Thank you. Okay, next up we have Murray and the Observers Group. If you have anything, I think he said he was good. No, he's not here. Alistair will take his place.
Very good. I think the next time I'm in one of these escape rooms, I'd like to have Dr. Hurd with me, because it's sort of like, okay, you're ready, start. Well, you're found your way out already. Amazing. Okay. Right. Okay. Welcome. Try and keep this short. Would like to invite those of you who are beginning your visual observing at the telescope, or with just your eyes looking out from your home, to come and join us at the Observers Group meetings that we have. With just a little bit of preamble for those who are thinking of buying a telescope, do not buy anything from Costco or Winners or whatever. Just had one of these Bushnell telescopes come into my hands, and at lower left is the actual usable parts from that telescope. So things like thumb screws and seriously. So the thing that at our eyepieces coming to our in-town groups for observing, and just come along whether you don't know anything about telescopes but would like to look through one, or need help using your telescopes. This is what we're here for. We also have a monthly Zoom chat, and we've moved the date from Wednesday to Tuesday to the third-ish one. So that's in a week, 8-day time frame. We're going to have a Zoom chat, and because it's probably going to be cold. But every now and then we get some nice evenings, and we have in-town gatherings. So please come keep an eye out on Facebook and come and have a look. Please also have a look at your Stardust newsletter. Murray has made a very nice article about some of the things that are up and visible in the sky to look for, and just 5-10 minutes of being outside under the skies and identifying some of these objects, bright stars, we'll get you the Explore the Universe certificate once we cycle through a year of these. And also for those of you who are not yet members, it's fine. Please come on out and share in the view of the telescopes. And we hope you'll really enjoy the sights you get out there. What we're still looking for, very little homework, go out, especially if you're a morning riser. It's not too early, it's still dark at 7 a.m. Having a look for P Corboreal. It's a star that hopefully will explode. Well, it's a little more complicated than that, but where to see it in the sky, Big Dipper, arc to Arcturus, and then this part of a Y-shaped thing, and it'll be here almost as bright as either Vega or Arcturus. And hopefully it will pop out. It's every 80 years or so that this thing goes off. So keep an eye out for that. When it's that bright, we've got probably a couple of weeks of it being visible to the unaided eye, and then a few months of following it in the telescope as it dims back down. So that's one thing to look for. And then the next one, I'm not sure why that's dark. Hopefully, am I pushing the wrong button? Yes, sorry. Other thing you will probably hear is that this is the week for the Geminid meteor shower. It is the best meteor shower of the year. The Perseids are fewer and fainter in comparison, but whatever the case is, you're not going to be seeing a Hollywood raining of shooting stars coming down from the sky. You get to see one every couple of minutes. Unfortunately, it looks like it's going to be cloudy. Thursday night is a little on the incoming shoulder, so it'll be tough. Yeah, this is the rain we're not going to get. Thanks, Frank. But just if you are out Thursday night, dress really warmly. It's going to be a cold one, and just keep an eye up in the sky, and maybe you'll see one of these lovely little meteors. We also have the Ursid meteors coming up on Monday, the 22nd, but it's a morning, late overnight. Ending on Monday, the 22nd. So those are also, if we get nice weather, hey, spend some time outside. The quadrantid meteors are a nice shower. Unfortunately, this year, full moon, so really don't bother trying for that. One thing I do recommend heavily here is looking for Jupiter moving. This is how much it moves compared to, there we go, Castor and Pollux in Gemini, two very bright stars, Jupiter being the brightest. And in 1 month, from this meeting to the next one, Jupiter will notch its way across. These are every 2 days or 2 nights, the motion. So sort of keep in mind that sort of hockey stick. If you've got binoculars, double check the position of these two stars, and you'll see it every sort of 3 nights. Oh yeah, it's shifted along. So something very easy for you to do without having to spend much time outside if it's really cold. Similarly, Uranus, very easy to find in binoculars. Everybody knows where the Pleiades are. Pretty much the most beautiful cluster in the entire sky. And your planetarium program will show you just straight down, depending on the time of night. But there'll be this neat little equilateral triangle of stars. And again, in 1 month, every 3 nights or so, it's like, oh yeah, it shifted over. So do have a look for those. And lastly, almost, if you know a high school student who would like to borrow a nice telescope, do get them in contact with me. We have a number of telescopes that have been donated, but the sort of beauty here is once you put it on a dolly, you can wheel it in and out of the garage in minutes. And we've got these things not to hand out to everybody, but a high school student can certainly borrow this and get some really nice views of the skies. And then very briefly, some National Society news. We have no fee hike this year. Yay! To help prevent increases in our fees, the Society would like you to think about ideas that might generate revenue. The more revenue we get, then it means our fees don't go up. And we're also looking for folks to submit nominations for awards. If you'd like to join the GA team, and especially if you have an interest in Canadian astronomy research and would like to write a little bi-monthly summary at sort of average reading level for the folks out here, please submit your name to the national office for doing that. So thank you much for your attention.
Thank you, Alex. Okay, get into a little bit of the trivia. And we'll take our break. Okay, I think we might have had this first one before. How long does it take for light from the sun to reach Earth? What gas makes up most of the sun? What phenomenon causes northern and southern light? What is the name given to our moon, and what is the name given to our sun? So we'll get to that after the break. In the meantime, let's take a quick break here. Try to keep it at 10 minutes because we got a fairly large astral imaging corner.
We also have membership pins. If anybody's looking for membership pins, I have checked.
Anyone who needs their membership pins, Tom Owen has them, so you can see him during the break. Okay, everyone, if we can sit down again, we get things moving again. We have a very large astral imaging selection tonight, so. Okay, we'll move into the announcement section next. Okay, so first thing we'll do is give us a casino update. We have a PowerPoint and video that Luke had prepared for us. Frank will get that going for us. Okay. Okay. So as you noticed on that, the casinos are major fundraising event of the every 2 years that goes to many projects that we have ongoing within Edmonton Center. So the other part of the announcements I have are that we are looking to fill 2 positions here. James McNeese, who's been our telescope loaner program coordinator for the last few years, is stepping down, and we need someone to replace him as the program director on this particular important feature that we offer for members and non-members alike. So if anybody is interested in stepping forward to take over that position, please get a hold of me. You can get me at the president@edmontonrath.com. And we're also still looking for a vice president. So if anyone's interested in stepping up to that position, just let me know at that same email address. And we can go from there. And so next on the agenda is Book of the Month with Mark Zelsick. And Mark, there he is.
Good evening. The library is located just as you go into the Star Theater, you just turn to the right and the library is there. It's open before and after the meetings. This month's Book of the Month was donated by Luca Vanzella. The End of Night, a deeply panoramic tour of the night, from its brightest spots to the darkest skies we have left. Paul Bogard restores our awareness of the spectacularly primal, wildly dark night sky and how has that influenced the human experience across everything from science to art. From Las Vegas's Luxor beam, the brightest single spot on the planet, to nights so starlit that the sky looks like snow, Bogard blends personal narrative, natural history, science and history to shed light on the importance of darkness and what we've lost, what we still have, and what we might regain, and the simple ways we can reduce the brightness of our nights tonight. So the book is available after the meeting if anyone wants to borrow the book. And some closing remarks regarding the season. And for that, we can call up the next slide. It's a clear Christmas night about 1 a.m. Whilst the party goes on inside the house, the family dog, an Australian cattle dog named Henbury, is led out to the south-facing back door for a bathroom break. Gazing up into the starlit sky, does Henbury catch sight of the blazing dog star twinkling to the south, about 20 degrees up? Christmas is the time for family gatherings, and caught up in the happy memories are the Christmases we enjoy with our dogs and cats. To highlight this loving relationship, I would like to share with you this Christmas poem. My dearest old friend, Oleg Skog, had me o'er for a cup of eggnog. I was promptly beset by his amorous pet, get off of my friggin' leg dog. Merry Christmas from Rosemary Bowl and I at the Lamplighter Library. Thank you.
Thanks, Mike. Okay, now, Astro Imaging Corner with Tom Olin.
Thanks very much. Why don't we just, Frank, maybe I'll just have you do the slides for me. Okay. You can put up the first slide. I'm so glad I don't have to do the fumbling this time. So, welcome to AIC 151. We have a lot of images tonight, in part because some couldn't be shown last month, because AIC 150, as you know, was a retrospective edition. And in this edition, I'm also going to experiment with a new, bigger format, except for it would unduly distort the image. So let's get going. Next slide, please. So this is a video by Alistair Ling, and I think, Frank, you can see at the bottom, if you just click on it, it doesn't have any sound. He says, this video is self-explanatory, I believe, no audio. It was captured at the U of A farm on November 11th. Very good, Alistair. Really enjoyed that. This is the Aurora Australis taken by Dave Mussel. Dave says that this image was taken on the night of November 16th from the Kaikoura Peninsula on the east coast of New Zealand's South Island, located at 42 degrees south latitude. This is a single 8-second exposure from a full-frame Sony A7R camera mounted on a Skywatcher Star Adventurer and fitted with an 18mm Zeiss lens at f2.8. Unknown to us at the time, there was a significant G1 rated geomagnetic storm predicted for the northern hemisphere that night, and bright aurora expected to be visible from unusually low latitudes in both hemispheres. This display was too dim to be noticed by us at that time and location, but it showed up clearly in the images. And we can go to the next slide. And this is his image annotated. So you can see besides the aurora, the image also shows the Magellanic Clouds, Crux, aka the Southern Cross, the bright star Canopus, several open clusters and globular clusters, including 57 Tacana, I'm not sure if I'm pronouncing that right, the massive Cana molecular cloud, and many others. Okay, that's terrific. We'll move to the next slide. This is Brian Alford, the Aurora. He says this photo is from the RASC event at Chikaku Recreation Area on October 30th, the eve of Halloween. The Northern Lights made an appearance. The photo was taken with an iPhone 14. Beautiful shot. Next slide, please. And this photo is also from the RASC event at Chikaku Recreation Area. The moon made kind of a spooktacular appearance as well. The photo of the moon was taken with a C-Star S50. All right, we'll move on. So this is a photo of Comet C/2025A6, aka Lemon, by Hans S. Johns. Named after its discoverer, the Mount Lemmon Observatory. I was able to collect 21 minutes just between sunset and clouds coming in on October 22nd with my NP127 IS telescope at 660 millimeter focal length. We'll move on. And this is Brian Martin's version of Comet Lemon. He said it would not cooperate. This is the best I was able to manage using the ZWO 294 MCOSC at 336 millimeter FL on a stellar view SV70 at focal ratio 4.8 and an AM5 mount. The comet was only 15 degrees above the western horizon, which looks over Edmonton from my location. Cloud and wind persisted each night I tried to image. Finally, on October 22nd, I managed 13 usable subs of 60-second duration through breaks in the cloud. Despite the short exposure and poor conditions, there's some interesting structure in the cometary tail. Well done, Brian. We astro imagers are a persistent lot. Move on to the next one. So this is from Alistair. It says 37 Nights of Mars. And he says, it may look like a Starlink chain, but it's not. This is Mars moving eastward against the background stars of Leo during a run of 37 nights in July of 2025. From Namibia, Leo sets on its head with Regulus at the lower left, its body somewhat upside down, with the tail at upper right. The displacement night to night was noticeable to the unaided eye. Well, that is just speaking of persistence, that is really an amazing image, Alistair. So this is from Daniel Tomsey, the question mark nebula. He says, hello, Astro Imaging Corner. I'd like to share my image of the question mark nebula. Over 70 hours of subs were stacked to generate this image, with over 40 hours dedicated to O3 imaging alone. The data was taken over 10 nights in August and September. This was a very challenging target to capture as it is quite faint, and my Bortle 9 location required a lot more integration time to get the details I was after. This image is not my usual SHO, but instead is in a 4-ax palette to emphasize the weak oxygen data. Bortle 9, Edmonton University campus. The mount was a ZWO AM5. The telescope was a Minicat 51. The imaging camera was an ASI 2600 mm Pro. The filters were an Antlia 36 millimeter 3 NM Pro SHO and LRGB V Pro Series R. He says, I hope the RASC members will appreciate the time that went into this one. Yes, we do. I mean, that's just that's a heroic effort and a great result. So congratulations. Next, Kent Martins. This is the Bubble Nebula, and you can see up in the top left, there's M52. Kent says the Bubble Nebula picture covers both M52 and NGC 7538 in a wider field than what is usually shown. I wanted to include both of those, plus the massive amount of gas and dust in the area. The camera is an OSC QHY 294 on an ASCAR 80 millimeter 4-element, and the mount was a Celestron CGX. Great shot, Kent. Oh, and I should say that it was processed in PixInsight using Russell Croman's excellent Exterminator tools, plus general hyperbolic stretch. I could use a hyperbolic stretch every now and again, you know. 26 lights of 180 seconds. Okay, so this is also the Bubble Nebula by Brian Martin. And he says, NGC 7635, aka the Bubble Nebula, image taken October 15th with the ZWO 294 MCOSC at 2000 millimeter FL, focal length using the RC10 Ritchie-Chrétien on a Paramount MX. The image is made from 110 2-minute unguided subs under very good atmospheric conditions from my Bortle 5 Plus site. This is a wonderful example of a bubble produced by the intense wind coming from a young, energetic central star. The nebula is located about 11,000 light years from Earth and measures about 7 light years across. And to get a 2-minute unguided sub at a 2000 millimeter focal length That's something that I could never do. So congratulations. That's amazing. And it's a great shot. Okay, next we're going to go on to Alan Hobbs, NGC 3372. On November 6th, and he says, on November 16th at Kaikoura, New Zealand, with my Seastar S50 in equatorial mode, using a Skywatcher wedge on the Seastar tripod, I centered the Seastar on NGC 3372 with 90 stacked subs of 20-second exposures for a total of 30 minutes exposure time. I processed this photo in PixInsight from the stacked FITS file. I was blown away by the richness of the nebulosity of this astrophoto, produced by the Seastar in equatorial mode. The Carina Nebula, or Eta Carinae Nebula, is a large, complex area of bright and dark nebulosity in the constellation Carina, located in the Carina-Sagittarius arm of the Milky Way galaxy. The nebula is approximately 8,500 light years from Earth. And I just think this photo shows it's just completely wild. I think it just shows the wildness and strangeness of things that we like to give cutesy names to. And I was railing about this in the break. We like to cut things down to our size, give them cutesy names, try to find the image that we think it looks like on Earth, and then move on. This thing kind of defies all that kind of stuff. All right, let's move on. This is the Cocoon Nebula, Kent Martins, and he says the Cocoon Nebula image includes part of the dark nebula B168. I thought it was more interesting to show the dark nebula as well. It certainly seems to be associated with the cocoon. The camera is an OSC QHY294 on an ASCAR 80mm 4-element Celestron CGX. Processed in PixInsight using Russell Croman's excellent exterminator tools, again, plus the general hyperbolic stretch. 19 lights of 240 seconds. And yeah, the Cocoon Nebula is very cool, and he's done a great job of capturing it. And there's even some of the dark nebula in the Cocoon Nebula itself, which you can see. Okay, let's move on. This is the Ray Weens's Eastern Veil. He said this was shot with the William Optics 132 and the ZWO 2600 MC with 250 subs at 120 seconds, and this was at the Northern Prairie Star Party. It was stacked in APP and processed in Lightroom, and I really think this is great. We love field-filling nebulas here at AIC. Well done. Let's move on then. And this is from Josephine Christensen, the Sol Nebula. She took it with her Seastar in mosaic mode, an hour and 33 minutes of 20-second exposures, AID noise in Seastar, and an auto edit in Lightroom app. Not much else done. Taken also at the Northern Prairie Star Party on September 20th, 2025. Cheers, Josephine. Well, cheers, Josephine. That's a great image. Thanks for contributing it. So this is M2. I was in Bucerias from Mexico, which is just north of Puerto Vallarta, from the 10th to the 24th. The skies there are Bortle 5, which aren't bad. This is the large globular cluster in Aquarius. It contains 150,000 stars and is estimated to be 13 billion years old. The image is a result of 60 10-second subs for a total exposure of 10 minutes using a 2600 MC Pro camera, a 90mm triplet telescope, and a 1.6x Takahashi TOA focal extender. The subs were stacked with Deep Sky Stacker and processed using Star Tools. Next. This is a contribution from Alan. As you see, the Milky Way and Magellanic Clouds. And he says, on a recent trip to New Zealand with Rick and Susan Bram, Dave and Carol Mussel, Marion and myself, after an observing tour, we went to do some wide field photography at the Church of the Good Shepherd at Lake Tekapo in a dark sky about 4:30 a.m. This shot was taken with my Canon 6D with a Rokinon 14 millimeter f2.5 lens set at ISO 3200 for a single frame 20-second exposure. The photo shows the large and small Magellanic Clouds, a near vertical Milky Way, with the Coalsack Dark Nebula beside the Southern Cross, with the Eta Carina Nebula above. Dawn was breaking in the southeast, illuminating the clouds behind the church. And isn't that a gorgeous shot? I think just amazing, and I love the blues in that color in that photo. So this is the Small Magellanic Cloud by Dave Mussel. And he said this image, taken from New Zealand's South Island, is of the Small Magellanic Cloud, the smaller of the two dwarf galaxies that accompany our own Milky Way. It is visible in the southern hemisphere, close to the zenith, high above the south celestial pole at this time of the year. It's located some 200,000 light years from our solar system and is home to numerous nebulae and globular clusters, many of which are routinely imaged by amateur astronomers. In the upper left region of the cloud, you can see NGC 346 and 371, visible as bluish smudges against the background stars. Both objects are considered stellar nurseries and contain numerous hot young stars. Lying 15,000 light years away, but in our line of sight towards the Small Magellanic Cloud, is the massive globular cluster 47 Tucanae. Seen to the right of the Small Magellanic Cloud, this object contains nearly 1 million stars and is the second brightest globular visible to us after Omega Centauri. The stars at the center are densely packed, many with separations less than a single light year. The night sky of a planet located near the center of 47 Tucanae would be an estimated 20 times brighter than our sky is because of the thousands of nearby bright stars that would be visible. This image was generated from 27 6-second subframes captured with the Sony A7R DSLR, equipped with a 100 millimeter Minolta macro lens at f2.8, mounted on a Skywatcher Star Adventurer. Though tricky to focus, macro lenses can be great for wide field astrophotography because of the sharpness and the flat image plane. Most of the processing of the subframes for this image was done in PixInsight, with final color and framing adjustments made in Apple Photos. This is Ray Weens's M31. It was shot on a ZWO 2600 with an APS-C sensor through the William Optics 132 millimeter telescope, 65 subs at 120 seconds in a Bortle 1 to 2 sky, and stacked in APP and processed in Lightroom. And a terrific shot, Ray. We can move on. And this is the M31 from Hans Johns. And he said this was imaged with my ASI 2600 MC Pro attached to a Celestron 9.25-inch Edge HD SET at 1650 millimeters. So it had a 0.7x reducer on it. So it was at f7.0. It was mounted on an iOptron CEM120 and auto-guided with a Celestron OAG. The location was his Bortle 7 and 8 backyard in Sherwood Park. As mentioned, I added data collected since 2023, which led to a total exposure time of about 11 hours in RGB with a Beta UV IR cut filter. I also collected 3.5 hours with an HA03 dual narrowband filter to add H-alpha data and bring out the galaxy's many beautiful emission nebulae. Image acquisition was controlled with Nina, and processing was done in PixSight. So we've been treated to 2 outstanding M31s tonight. And we've got another one coming up. Nope, we do not. This is M33, of course. This is from Brian. Messier 33 is a fall favorite, he says. This is an image taken on October 14th with a ZWO 294 MCOSC at 2000 millimeters focal length using the RC10 Ritchie Chrétien on a Paramount MX. The image is made from 55 2-minute unguided subs. A distinctive feature of this galaxy is its lack of a central core or massive central black hole. Studies of this galaxy suggest that its morphology is strongly influenced by a large halo of dark matter, and thus M33 has become an important test on the nature of dark matter and the role dark matter plays in the structure of the universe. This is a really great image, and I know from experience, M33 is a challenging object to photograph, and Brian, you did a great job. So this is another image from my time in Mexico, in Bucerias, north of Puerto Vallarta. This is NGC 253, aka the Sculptor Galaxy. The telescope was a 90 millimeter TS Optics triplet with the Takahashi TOA 1.6x focal extender. And again, the camera was a ZWO ASI 2600 MC Pro, approximately 4 hours of 1 minute and 2 minute subs. And the subs were stacked with Deep Sky Stacker and processed using star tools. The image was cropped to remove stacking artifacts. I'd always wanted to capture this object, and I'm happy that I did. So thank you to all our dedicated astro imagers, including those just starting out. I encourage you, if you're starting out, to submit your images. We all want to see how you're doing. And this is a difficult hobby, and it's good to get great feedback and encouragement. So I encourage you all to submit. Thanks very much.
Thank you, Tom. There's some great images I know today. Okay. So we can get back to the agenda. We'll go to the trivia answers. So how long does it take for the sunlight to reach Earth? 8 minutes, 20 seconds. What gas makes up most of the sun? Hydrogen. What the phenomenon causes the northern and southern lights? Solar wind interacting with the Earth's magnetic field. The name of our moon is Luna, from Latin, and the same with even our sun is Sol. A lot of people don't know those last two. Okay, we'll go to final announcements. Go to the cartoon. Now, I think everybody's probably felt about that first one. I think Frank wouldn't mind and Jeff wouldn't mind seeing some of those trees on the southern side of the Coronation Park decapitated slightly. As our deck, the trees over on the south end are starting to block a lot of the lower part of the sky at night. And I know a lot of people are wondering when they're doing their after photography, did I connect everything correctly? Yeah, that's why I went with a C star. Okay. Okay, so the next meeting is Monday, January 12th, 2026. This will be our AGM and regular meeting, and will also be a members' night. So any member who wants to do a presentation on that evening, please forward that information to me, and we can get it on the agenda for next month. The AGM this year is not an election year, so basically it will be our final financial report, auditor report, and anything else we come up with prior to that we think need to be brought up. So again, it's the holiday season, so it's the last meeting of the year. So I'm wishing everyone happy holidays and a happy new year, and we will see you in the new year. Thank you.